Hello friends, welcome to Cadence tutorial. I am Madan Kumar Jha and today in this lecture series I am going to explain about how to evaluate noise margin, static power, switching frequency and propagation delay of an inverter, and I will also see how to change the width of a PMOS to make the VTC curve aligned with VM. Uh, so first I will show that, and then I will explain how we can evaluate the static power and dynamic power and these things. Okay, so go to I have made this schematic of an inverter in my previous video, so you can watch there. So in this lecture I am only going to show you these parameter evaluations. So go to launch, then in ADL go to analysis, then click on edit, then set DC analysis, then select on component parameter, then click on select component and then select input voltage because I want to plot BDC curve. So then click on OK. So it will give you a BTC curve. Okay, so the input voltage range should be 0 to 1.8 volt for BTC curve. So I am going to set this, then go to ADL. On output section click on edit, then from design you should select this input A and this Y. Okay, then click on OK. Actually I have made the width of this PMOS as variable W. How I have made it variable? Escape, then click on this PMOS, then press Q. Then in this parameter you should change this width from 2 micrometer to WM, which will be W meter. So now I have to assign this width in micrometer in design variables. So here click on OK, then go to ADL, and here right click on design variable, then copy from Sylvie. You will get W, which is the variable. So set this width to 20 or 10 micrometer. Okay, so in starting you can assign any kind of value here. Okay, then go to analysis, sorry, tools, then in parametric analysis you should copy the variable which will be W, then go to from and to, and then in from and to you have to set here the range of this W, so which range you want to choose. So actually I want to set the BM. So before doing parametric analysis I am going to show you the BTC curve of this PMOS at 2 micrometer. Okay, so you can see here when the width is 2 micrometer, which is automatically set in PMOS, like when you will press I, and when you will go to instance and then in GPDK 180, GPDK 180, and if you will search for PMOS, then you got that the size of this PMOS, the width of this PMOS is 2 micrometer automatically. So if I will use it here, then it will be 2 micrometer. So first I want to see the BTC curve when NMOS width is also 2 micrometer and PMOS width is also 2 micrometer. So in this case you will get that uh, the BTC curve will be, the BM of BTC curve will not align with 0.9 volt, which is half of the voltage of VDD. Okay, so I will tell you why it should be half of this BTD. So I'm going to change this style to solid. Okay, so press B for vertical line and then drag this vertical line to 0.9 volt. So you can see here it is 900 millivolt, or you can also see there. Okay, so this is basically 900 millivolt, which is 0.9 volt. Okay, so this is 900 millivolt, but your BM is this is 0.9 millivolt. Okay, but at 900 millivolt it is not aligning with this. Okay, it is not aligning with this. So what you should do, you should change the width of this PMOS or NMOS such that this BTC curve BM, that is half of this BTC curve, should be aligned with 0.9 volt. Okay, so you can see this is 900 millivolt. Okay, so here the curve should be here. Okay, like this, but my curve is here, so I have to change the width of this PMOS such that this BTC curve should be aligned with this. Why this is required? Because of the following reason. If you will change the width and if you will align this BM with this with the BM of this BTC curve with this 900 millivolt, that is half of the BTD, then there will be several benefit, like the noise margin NML, noise margin low and noise margin high, will be equalized. And then there will be some benefit, like if the noise margin NMH and MNL will be equalized, then there are when you change the logic 1 and logic 0, and then your PMOS, your inverter will be equal tending towards 0 and equal tending towards 1. Okay, when you supply input voltage 0, it will gives uh, output 1 for 0.9 or for half of the VDD value, till half of the VDD value. Okay, so this is one benefit, and the second benefit is for noise suppression. So when you will use some noise in input voltage, then that input voltage will be suppressed in extent to that NMH or NML. Okay, so these are several benefits of this uh, of aligning this inverter BTC BM with the half of the VDD voltage. So if you want to know more about this, then you can go to book and you can study from here, or in your 30 class you'll get that. But in this video I will show you how I can align this with that using parametric analysis and all those things. Okay, so close it. Then so I have to set this PMOS voltage, PMOS width to some extent such that it the BTC curve maximum voltage BM should be overlap with that 0.9 volt. So for that I make it variable and I am going to do its parametric analysis from 2 micrometer to 10 micrometer. Okay, I am going to change the step mode to linear and step size to 10. and then run the simulations. So you can see this is the simulation of this parametric analysis. Now you can observe here that when I have let me make it more wider. Okay, so now you can see when this BM is 1.900 millivolt, that is at this point, this curve is look like aligned with this. So at that time the width is 7.33 micrometer. So if I will use this width 7.33 micrometer uh, to the PMOS, then at that time it will be aligned with 0.9 millivolt. Not exactly aligned, but it look like aligned here. So you can see it should be here. Okay, it should be here, sorry, here, but it is somehow far differ from this. So when it will be aligned with this, then uh, that width should be set into the width of the PMOS. Okay, and it will give the minimum noise margin for or it will give the equalized noise margin MLN and MLH. Okay, so this is the one way to do this, but there is also a secondary way on which you will exactly get the width of this PMOS for this 0.9 volt. So what should we do? I should go to ADEL. Okay, then in ADEL go to tools and then click on calculator, then click on this BS, then go to, after clicking on BS, go to your schematic and select the output node Y, then click on functions, and in function panel you should search for cross. So this cross function will use for calculating that variable for 0.9 threshold voltage. So if you set the threshold voltage at 0.6 or 0 anything, then it will give the width of that PMOS in corresponding to that value. But I want to set it 0.9 because I want to check the width for BM. Okay, width of PMOS for BM, that is 0.9 volt. So I am going to click on apply, then in OK, and after click on OK, you will get this function here. Then you have to append it, or you want this on your ADL. So click here, it will send this expression to AD outputs. Okay, so click on this, then you will get that in your ADL window. Where is your ADL window? Yeah, I think this one. Yeah, so here you will get these expressions. So now this time uncheck this two plot and only check this one, and then go to parametric analysis and then run. Okay, so when you run this parametric analysis, then you will get the value of this W for 0.9 volt input voltage. Okay, so wait for simulation. Okay, So here you can observe that at 900 millivolt, this is 900, okay. So at 900 millivolt, the value of, yeah, this is 900. So at 900 millivolt, the value of PMOS is 7.47, okay. So the value of 7.4744, the value of width of PMOS 7.4744 micrometer will give you aligning of that BM with half BDD by 2 or half of BDD, okay. So close this, go uh, there in schematic, okay. So escape, or you can change it from here also. So go there, remove this parametric analysis. Now go here and set it 7.47, 7.474, okay, and run this. Now uncheck this, okay. Now run this. So I'm going to change this style to solid. Now you can see here at 0.9 volt, okay. Here when VDD is 0.9 and this voltage is 0.9, all A uh, yeah, this BM by 2 is also aligned with this 900 millivolt, okay. So this 900 and 900 millivolt is aligned with this BM by 2, okay. But in previous case it is something like here, okay. So now it will give you a equal noise margin for NMH and NML, okay. So you can calculate the noise margin from the formula of uh, this NMH equals to BOH minus BIH and VIL minus BOL. So what is BOH and BIH you will get from this curve. So basically this is BOH. Actually BOH is basically 1.8 volt or BDD, or BOH is when the slope of this BTC curve is -1 here, then the output voltage corresponding to that -1 slope, okay, will give you BOH, and the input voltage at that 0. At that minus 1 at that negative slope of -1 will give you the expression of BIH or the value of BIH, and this minus the slope of this the BTC curve at -1 will give you BIL, sorry, BOL at y axis, that is output axis, and then this expression will be BIL, okay. So I am going to write it here, okay. So VOH equal to VOH equal to VOH equals to mm, I think it will be the negative slope, so it is approximately 792 millivolt, sorry, 1.65 millivolt, okay. So 1.65 millivolt is corresponding to VOH, or it gives VOH. So 1.65, or you can take it approximately 1.8 volt also. So sometimes people use directly 1.8 volt, but I am going to use this 1.6568. So 1.6568 will be VUH. 1.6568 is your VUH, then comma VOL. So VOL will be this. So let's assume that it is negative slope of -1. So in this case VOL will be on y-axis. So the voltage at y-axis is 138 millivolt. So I'm going to write here 138 millivolt equal to 0.138 volt. Okay, so it will be your VOL comma BIH. So what will be the BIH? So BIH will be the value when it will be -1, the slope will be -1, and at that time the input voltage is your BIH. It is the maximum input voltage at logic high. So it is 1.59722 volt. Okay, sorry, it is not 1.59, it is at 792. Okay, so 792 millivolt, it is 792 millivolt. 792 millivolt equal to 0.792 volt. Okay, comma BIL. So BIL equals to, so let me write it here. Okay, now BIL is equals to, you can observe it from BTC curve. So what will be the value of BIL? So BIL is this. So actually BUL is 0.138 volts. So I have taken -1 slope at 0.138. So 138 I have to, so at 138 millivolt the value of BIL is 982.59. 982.59. Okay, so 982, so 0.9, sorry, 982. Okay, 0.982 volt. Okay, will be your VIL. So now you can calculate noise margin, which is approximately equal to BOH minus BIH, which will be 1.65 1.6568 minus VIH is 0.792 volt, which will give you 0.8648 volt. Okay, and then what will be the BUL? Sorry, NML. So NML is equals to BIL minus BUL. So BIL is 0.982. So 0.982 minus BIL minus BOL. BOL is basically 0.138. So it will give you 0.844. 844. Oh, 0.844 volt. Okay, so you can see here the NMH and NML is approximately equal to, actually I have taken roughly the slope of -1, not exactly. So why it vary from some millivolt, but in actual case it is exactly equal. NMH and NML should be exactly equal. So you can see here also that NMH and NML is equal. So by equalizing this NMH and NML you can get many advantage of that NMOS. Okay, sorry, that inverter. So this way you can find noise margin. Then for finding the dynamic power of a inverter, you should use one load capacitance CL, then VDD is 1.8 volt, and the switching frequency will be your transient frequency, sorry, your period of that, 1 by period of that V pulse you will be using in the input of that inverter. Okay, so that will be your frequency, so you can calculate your dynamic power from there. Then you can use a resistive load RL, and that resistive load RL value will be given, and BOL you can calculate it from that BTC curve. Okay, by plotting that BTC curve, or if you want to a separate video for this resistive load inverter, then I will make it in next part. But you can also find by yourself. This BDD is already known, BOL you can know from BTC curve, RL is already specified or given. Then you can calculate this static power as BDD into I. Then dynamic power, you actually CL will be given, BDD is also given, and frequency will also given. So you can set B pulse according to this frequency. If frequency is 100 megahertz, then you have to select that B pulse equals to 1 by 100 megahertz, and the period of that B pulse will be 1 by 100 megahertz. Okay, so you can do that all things. Noise margin can be calculated. That this propagation delay. So for propagation delay, you have to give the right time to that B pulse. Okay, and for that right time in B pulse, there will be some fall time at output of that inverter. Okay, sorry, when you give the right time to the input of that B pulse. Okay, so in output section also you will get some fall time. So the midpoint of that fall time and the midpoint of that right time of input and fall time of output will give you tPHL, that is t propagation high to low. Okay, similarly you can find tPLH, t propagation low to high, from the fall time of input and 50% of right time of output. Okay, so by calculating this tPHL and tPLH, you can find your total propagation delay tPHL plus tPLH by 2. So this is the all about CMOS inverter analysis of some power, frequency, and how I can change the width of that PMOS for getting a equalized noise margin. So thank you for your patience. I will see you in next lecture.